Okay, jump on into some thermochemistry. Thermo. So, a couple areas of chemistry that we're going to dabble in this semester, and we're going to pick up in a much deeper way next semester. One of the ones I've talked about already is titration. We are going to do a titration tomorrow with titration of vinegar. It is posted, so make sure you're free lab and turn off the lab or bring your laptop or whatever. So we're going to titrate the polarity of an unknown with a burette. So it's going to be kind of a fun lab. The other area that we really just dabble in and we don't get to the bottom of it until next semester is this area here, thermochemistry. There is thermochemistry. We are going to talk about the movement of heat today. We're going to derive the equation for enthalpy. We will use enthalpy in lab next week. I think that's Dr. Harris's first lab he'll be teaching. But we don't really land the plane in here until next semester when we get to Gibbs-free energy. Because we have to talk about enthalpy and entropy, and that brings together the entire picture of Gibbs-free energy delta G. And that's really what we want to get to, but we're not going to tackle that until next semester. But we do have to have enough thermochemistry to understand how it is that heat moves. So what we're going to talk about today, what our worksheet is today, is the movement of heat. Heat always moves from a hot body to a cold body. That's because heat is something, it's motion. That motion translates to a polar object, and it brings motion to the other polar object, which is the transfer of heat, heat being motion. Now, that being said, there's an incredible amount of energy stored within food, and that's why we eat food. So something like this glorious double-double right here is going to have protein, fat, and carbs in it, right? Various creations of mankind right there. So we're going to take the cheese, which is going to have probably some sugars in it like lactose. And as American cheese, processed cheese is probably mostly carbs, okay? Be some fats in there. So how is it that I take a big giant molecule like a fat, and I'll show you the one that's in beef tallow. It's this molecule here, and I'll give it to you in the abbreviated form. Okay? So it basically looks like this. 2, 4, 6, 8, 10, 12, 14, 16, 18. Nailed it. That is the fat that's in beef. So when you're cooking hamburger and you strain off that grease and you put it in the can or whatever and it starts to solidify and become that white solid, it's because this is a solid at room temperature. It is a liquid when you heat it up. But what happens to fat is our bodies take fat and enzymatically, through enzymes, they convert it to carbon dioxide, water, and energy, all right? Carbon dioxide, water, and energy, they burn it. And we do that basically through the citric acid cycle. Some of you might know it as the Krebs cycle. So I can take fats, my body enzymatic can break those down and harvest the electrons between each of these carbons, because each of these carbons here has a pair of electrons. A pair of electrons between that carbon. And there's a carbon there with a pair of electrons. And that carbon there has a pair of electrons. And that carbon there, you get the point. All these bonds are pairs of electrons. And if I can harness the electrons between the carbons, there's actually quite a bit of energy in there. Those of you that drove your vehicle today, there's some of this in there. Okay, 2, 4, 6, 8. This is called octane. All right, octane also oxidizes to carbon dioxide and water and energy. We are no different. The only difference between us and the automobile's doing it at a quite high temperature, around 400 degrees. Okay, we are doing it at a lot cooler temperature. We are doing it at 98.6 unless we have a fever. So how do we burn this in a controlled environment without burning up the body? Because organic molecules are very delicate. Up over about 180, they decompose. So our body does it through a series of enzyme steps. All right, so we can do fats. We can do sugars. So we might actually do sugars. And so a sugar is going to also look like this. So this is going to be alpha D-glucose, which is the #1 sugar that the body uses. It also enzymatically goes to carbon dioxide, water, and guess what? Energy. Okay, pretty cool. So those are the two main sources of the thermodynamics within the body. How is it that I can take something and convert, whether it's the carbohydrates, the sugars, or amylase or amylopectin, or some of these larger polymers of glucose, or if I can take the fats in there, and we can also even take the proteins and burn those. Our body typically doesn't unless it's under starvation or you're on a ketosis diet or some kind of special diet. For the most part, most of us are fueled by carbohydrates and fat. But how is it then that I can take those and translate those into energy? That's what this chapter deals with. It's actually a very pragmatic or very practical chapter on the movement of heat. But before we'll understand the movement of heat, we have to understand a little bit of physics. Yay! So all of you want to know about potential and kinetic energy, so let's go ahead and get the ball rolling, so to speak. Energy is the ability to do work and heat. Okay? Thankfully, in here, we're going to get rid of work. We don't do a lot of mechanical work in chemistry. Save that for the engineer and the physicist. Most of what chemists deal with is the heat movement, which does become very important. So how is it that we move heat from one object to another object? As I said, heat always moves from the hotter object to the colder object. I'm going to work a couple problems with you on this because, again, this is where it gets a little bit, it's not difficult, but you have to think about what heat is and what it is not. Okay, so around things like endothermic, exothermic, system, surrounding. We have to keep track of some words here. So it is going to take some time in the trenches to learn these words and what we're talking about, so we have an understanding of thermodynamics. Now, my chemistry majors will take this to have a whole semester of nothing but thermodynamics. So we're just going to skim over the top and have a basic knowledge of this. We're not going to drill down like my chemistry majors will have a really good handle of this with Dr. Harris, who teaches the thermodynamics class. So again, thermochemistry, the transfer of heat from one object to the next. How is it that I transfer heat from something like tallow, fat, beef fat? How do I transfer this energy, this heat? How is it transferred? Okay, how is it stored? That's another thing that is an important process in ADP going to ATP, which is, of course, the storage of it. So we're going to talk about different metals. They're going to have things called heat capacity. How much heat can a certain metal have? Okay, some metals have a better heat transfer. That's why on the back of a computer, oftentimes it's aluminum, because aluminum gives off energy quickly. But if you're cooking, you don't want that heat transfer too fast, so you're going to use something like a copper or copper core is what I use. Those alclad copper cores is what I use. They're about $300 a pan. So they're very expensive cookware because, again, this is all, cooking is just about heat transfer from the energy source into the sugars and the breakdown of the sugars and the carbohydrates, and that's where you get all your flavorings and fats and deliciousness. Okay, so two different types of energy. There's kinetic and there's potential. Potential, of course, is stored energy. That cheeseburger back there had an incredible amount of potential energy. And it doesn't become kinetic until I eat it and then I go on a jog or something to convert it into motion. All right? But it has a lot of energy stored in the fats and the carbs and the proteins themselves. All right? So the kinetic energy equation, expression that we often use, very simple. Some of you, again, if you've had physics, this is a very standard equation. Will you have to memorize it? No, you will not. But you need to understand it. Energy kinetic is half times this mv is going to be the mass or the weight of this object times the velocity squared. Okay? How heavy is the object? How fast is the object moving? Squared gives us the energy in kinetic. Okay? Now, potential energy is the energy that is in storage. That's most of the time what we're going to be working with in chemistry is how much potential energy is stored in certain molecules. And can we calculate those? And on Wednesday, we'll see Hess's law. And Hess's law helps us calculate these with fairly good accuracy of getting energy out of kilocalories and calories out of compounds. Okay? Now, the difference between the two different equations is because potential energy is the energy of, when we take the potential is the stored energy. So really what we're talking about here is the electrostatic potential of this. How much energy is actually stored between the atoms, which is exactly what's going on if you go back to our fatty acid up here. There's energy stored between these two carbons. The question is how much energy. There's also energy stored between the two hydrogens that are on it and the other hydrogen. There's energy associated with all those electrons, right? But the question, how much energy? Well, That's where we have to have two different charges separated by a certain distance. Depending on how much is separated here depends on the energy potential stored between those. So we typically think about these as more of these vectors, if you will, of electrostatic attraction. Now, I know that's a lot of blah, blah, blah in a mouthful. This will come full circle the first part of next semester when Dr. Harris talks about lattice energies and the Coulomb attractions there. That'll become very important. So that, again, that will come back to us. For now, we're not really that worried about the potential energy stored in that. Okay? Until we get to molecules, of course. Now, in this, we typically are going to use the joule. 1 calorie, you do need to memorize 1 calorie equals 4.184 joules. You need to just memorize that. It's an exact number. We have to have that because we use the joule today. But man, a lot of the calculations that we do in the actual laboratory in the chemical rubber company, that big massive book that I showed you in the lab, a lot of them still have kcals in it. Okay, kilocalorie is an old school way of quantifying energy, but we still see it quite a bit. So again, this one, we just need to have that in our working knowledge, okay? 1 calorie equals 4.184 joules. And by the way, this is not the calorie that you find on the calorie count on the back of a label. That's off by a factor of 1,000, but I don't really care about that. This isn't a class of nutrition, but that is, the food calorie is actually 1 kilocalorie. Again, which is oftentimes what we actually see in these tables are either kilocalories or joules. So joules are what we're going to typically use in here. 1 joule, if you look at it, is a kilogram meter squared per second squared. Kind of a funny way of thinking about energy, but that's what it is. Mass, okay, kilogram, and you can see that we have this movement of mass through the Cartesian coordinates of life. Kind of funny way of thinking of energy. That's kind of cool. Okay, so definitions, system and surrounding. Number 1, the system is where the reaction is taking place. Okay, if we're next Tuesday when we actually do bomb calorimetry in our little styrofoam cups, everything inside the cup is the system. The water, the chemistry that's going on in there, the heat, movement, that's the system inside there. Everything else is the surrounding, okay? So the surrounding, everything else. So in this case, the red and the white compounds here, the hydrogen and the oxygen, are the system. They're what we are going to react in this piston-driven reaction that's going to produce water and energy. And the surrounding is everything else. Now here's why that's important. We're going to break this down into heat flow. So heat is going to flow either from the system to the surrounding or from the surrounding back into the system. Okay? So we're really talking about the flow of heat. So we have to say we're talking the system or the surrounding or the system. And here's the way you kind of want to think about this. The environment and the system, or the surrounding, as I called it here, the surrounding and the system, here it's called the environment or the system. So we can either do work on or move heat between. Like I said, we're not going to concern ourselves with work, okay? So this part of the equation, the work, is going to quickly disappear. And I'll show you how that works. It magically disappears if we do a little bit of math trickery. Now we can get rid of work, because like I said, typically chemists are not worried about piston movement. That's more engineering or physics. Chemists really want to know energy content and potential energy stored within lattices or organic molecules up here on the board. So our part of the equation that we care about is down here. All right. So somehow we're going to get rid of work, and we're going to have a new symbol for energy called H, or enthalpy. How do we get there? Well, we will get there. Just trust me. All right. So in a system like this, notice you have an initial and a final. Okay? Sometimes that heat or that energy is going to be higher initially and lower in the end, which we are going to call exothermic. Sometimes we have an initial energy and we have more energy out in the end. We'll call that endothermic or endergonic. All right? So depending on whether my final and my initial has more energy or less energy, depends on the state, well, we'll call a state function, but the movement of that energy through the system to the surrounding, okay? So here you can see, here, energy was gained from surroundings to the system. we move from the surrounding to the system. So we started lower energy and we ended with higher energy. So if I'm the system and I've increased in energy, energy has to come from somewhere. So it came from the surrounding to the system. If I am the system and I've given energy off to the surroundings, or my final energy is lower than my starting energy because I've moved energy from myself to the system. Okay? So we have exergonic and endergonic, or exothermic and endothermic. Those are our two typical words that we use in here. If it required energy from the surrounding, it's endothermic. If it gave off energy to the surrounding, it's exothermic. Okay? So really what we care about is internal energy. It's the sum of all the kinetic, because we don't really know the true total energy of a system. All we really know is the difference. That's why Hess's law actually works. It's really hard to know exactly how much energy is in something, but what we can quantify is how much energy transfers from the system to the surrounding. So that's why we typically think of it as an initial phase, or initial, and a final. Now, this is going to get a little bit spicy when we start to have energy actually, or heat actually flow through. And I'm going to try my best to explain this, because you have to think about, if I'm the system and I'm the surrounding, my initial state, if I've moved energy, is going to be backwards. Okay, and I'll explain what I mean by that. So sometimes it's going to be final minus initial, other times it's going to be initial minus final. Most of the time, if you're going to guess, it's final minus initial. But if I'm flowing, then one of them has actually gone the other direction, and I'll explain that when we get to those problems, okay? So here we go. If the change in energy, if my final energy is greater than my initial energy, it's this one here, okay? We call that endergonic or endothermic. If my change in energy, my final is less than my initial here, we call that exergonic or exothermic. Exo, giving off energy. The system gave energy outside of exoskeleton, exothermic. Okay, endergonic, endothermic. All right, endoskeleton, like we have. So you can see that those are, again, the movement of energy from system to surrounding or surrounding to system. Okay, those are your two choices. What's going to complicate this next semester is we also have to bring in entropy. Entropy is the quantification of the randomness of the system. So again, Dr. Harris will flesh all that out and help you understand Gibbs free energy. But for now, we're just going to talk about heat. Okay? So let's derive the heat equation, shall we? I know that the difference in energy, change in energy, is either going to be given off through heat or through motion or work. Okay? Those are the two ways that energy can move from the system to the surrounding back to the system. Either through work or through heat. Okay? And like I said, we're going to get rid of work. We don't want that. We're going to keep our piston solid. We're not going to have this thing moving up and down in mechanical energy. Okay? So, again, heat from the surrounding to the system or from the system to the surrounding. Heat. So heat equals, change in energy equals heat plus work, the amount of work done. All right? Now, this is a weird thing. If I am the system and I have given off energy, you are going to feel that as hot. Right? If you put a log on the fire, and the fire is the system, what does the surrounding feel? It feels that heat from the burning of the cellulose. Okay? That's what wood's made out of. All right? So heat is given off. But if the surrounding has given heat to the system, what's the sensation? It's going to be cold. Now you have to think that through. If the surrounding gave heat back to me, why do I have the sensation of cold? Because it's the opposite of the system giving off heat to the surrounding, which feels hot. Okay? And that's how cold packs work. Cold packs are an actual chemical reaction that actually takes place and actually absorbs energy from the surrounding to the system, so it has a sensation of being cold. Likewise, we can do the other way around, right? We can have a hot pack. Or we can break something up in a chemical reaction and the pack gets warm or hot. All right? So again, one's exothermic, giving off heat, one's endothermic, accepting heat from the system or the surrounding. Okay? So we can go either way with the chemistry of either exothermic or endothermic reactions. Now, I'm going to hold off on that one. I'm going to come back to that. That's one for my Gibbs. So here's what we want to think about. Because energy is being released here, okay, it either can be released this way through a little bit of heat and work if I'm going to turn a fan, or it can be released all as heat. All right. So like I keep saying, we're going to concern ourselves with heat, not the work part of this. So we've got to get rid of this W, this work part, the work function of this equation. All right. Now, I know that work, and you don't have to memorize this, just trust me for it. I know that work equals, and when we get to the gas laws here, not too far out, we work with our P equals nRT gas laws, you see that work equals the negative P of delta V. Okay? So work equals pressure and difference in volume. And that should make sense. Because that's movement, that's mechanical work. That's how pistons actually work. To the greatest inventions that led to so many of our modern day inventions is hydraulic, which is P delta V, and piston, which is P delta V. Okay? So if you think about that, the combustion engine and the piston and the hydraulics that move these massive machinery is actually pretty remarkable engineering, and those are two of the greatest modern inventions right there. But we know that the work is going to be negative of the pressure times delta V. Okay? Now, enthalpy is the internal energy plus the product of pressure and volume. So that equation looks like this. Enthalpy, H, is the energy plus the change in PV. Okay? So you think about add it to the pressure and volume. So let's derive this. You want me to go back? Someone's actually trying to take notes. So what we're going to do is we're going to substitute into our equation for the pressure-volume relationship, and we're going to see that at the end we can have Q, heat, equal this new enthalpy value. That's where we're headed, and that's all you really need to know with this equation. I'm not going to have you derive it. I just want to show you how it is derived. It's kind of cool. Okay? So again, enthalpy. Enthalpy is H. Gibbs free energy is G. So we're going to be working with H, enthalpies. All right? So here's what it looks like. Change in enthalpy is the change in energy plus PV. Well, wait a minute. Well, what was work? Well, work, if you remember, was right here. Where'd my work go? Where's my work? There it is. Work equals negative P delta V. Well, wait a minute. Check this out. If I rearrange this equation, multiply each by delta, delta E, delta E, delta PV, delta PV. Hey, I know that work equals negative P delta V. That's kind of cool. Those things look a lot alike. Therefore, if I take the delta H, delta E, P delta V, substitute in Q plus W minus W, I end up with, hey, wait for it, work. So heat. So enthalpy is the movement of heat. All that to get to that, all right? So all you need to memorize is delta H equals heat. That's the equation that we will focus on and we will use. Now, it has a couple variations, and that's what we need to talk about next. But ultimately, enthalpy is a quantization of the movement of heat. System, surrounding, system. There we go. There's where we're at. Okay? Now, this assumes constant pressure. That is one of the assumptions. If you change the pressure, now you're going to do some work, so that changes it. So what we're going to do is we're going to assume that our pressure has been standardized, all right, or held constant. So constant. If we do that, we then can quantify heat. And what's really cool, honestly, is the lab that we do next week when we just use two little styrofoam cups. We get great data out of this. You're going to get to see some really neat data come out of the heat flow from our system to the surrounding. It's really fun experiment to actually get to see this take place. It's super cool. Okay? All right, so here we are. Endothermic, exothermic. Boom, just like that. Now, the change in enthalpy is going to be product minus reactant. Product minus reactant, or final minus initial. Okay? So my change in enthalpy is going to be the enthalpy of the products minus the enthalpy of the reactants. Because now we're going to start to do chemistry using our enthalpies, which is heat flow. And that's the whole first part of this is more the physics side of deriving this. Now we're going to put it to practical use and actually use this to calculate heat, okay, or enthalpy. All right, so a couple new terms: enthalpy of reaction and heats of reaction. Okay, so depending on what we're talking about, we have to know what capacity of heat for a certain object is. Wood has a different heat capacity, something like aluminum or copper or steel or water or gold. All right, they all have a level of heat that they can hold and that they can have flow through them, and the rate that they flow through is very different. So we have to have a way of quantifying that in order to know what we're talking about when we're talking about this heat movement. Okay, so with that we have two specific terms. I know a lot of terms here. Think of all the terms you've already learned, right? Kinetic potential, system, surrounding, endothermic, exothermic, right? Now we've got enthalpy and heat. A lot here. Okay? Now we're going to add two more to it. Specific heat up here and heat capacity. So what we have here is the specific heat capacity of certain compounds. Typically we're going to use specific heat capacity or specific heat. That's what we typically use. Heat capacity is really more of a subset of this. For us, most of the time what we're going to use is what we call the heat capacity. Heat capacity has been standardized because we have to know, again, what are we talking about? What are we relative to? Just like carbon 12 is the periodic table, this has been standardized to the amount of heat required to raise the temperature of 1 gram of a substance by 1 Kelvin. Okay, that's just by definition. So how much heat does it take to raise the temperature of 1 gram of gold 1 Kelvin? How much does it take to raise 1 gram of water 1 degree? All right, and so you can see these numbers here have all been measured. So uranium, here's water, 4.1813. Does that sound familiar? Oh, that's kind of cool. Okay, so water, steam, you have steel, oxygen, lead, copper. Where's my copper? This one doesn't have copper on it. Aluminum, look at aluminum, it's really low. And that's why they use it as fins on the back of something for cooling agents, because it gives off energy real fast. Whereas something like uranium, uranium's pretty low too, but where's my high one? Right, polyethylene, like a Nalgene jug or Nalgene bottle. Look at hydrogen's capacity, massive. That's pretty cool. So you have to have that table. You just have to have a table, and that data will be given to you. It's not like you have to memorize this stuff. But you can actually find this in the CRC, in the laboratory. All this data is in there. It's all been calculated, it's all been determined, and we just use the data. Okay? So again, we're going to use what we call specific heat capacities in this. So here's what it looks like. Specific heat, C sub S, specific heat, so what we're going to be using out of the table, equals Q, or the heat transferred, over the quantity times the change in temperature. Now that's an important equation. This is an important equation. So specific heat is the heat transferred times mass over the temperature change. Okay, so that's what our specific heat looks like. So here's the way the questions will be worded on a cheat or an exam or a quiz. How much heat in joules will be required to raise the temperature of 200 grams of iron with a specific heat of 0.451 joules per gram per degree centigrade from 12 degrees to 400 degrees. So basically how much is how much heat is it going to cost me to heat up a steel rod or a knife or some kind of metal object that's made out of iron? All right, and so you can see that this is how we're going to calculate this. So how much heat? Heat is Q, right? So we have to calculate that by moving m delta T over on the left side, and we can calculate that. So if we rearrange the equation, Q equals C sub S times mass, boom, times the change in temperature. Well remember, delta T is final minus initial. So I'm ready to roll. I have my specific heat, Okay, right here for iron, I have the amount of iron, and I have the change in temperature. I'm going from 400 I'm going from 12 degrees to 400. All right, so let's think about this. How much heat is going to be required? Well, when we plug it all in, 0.451 joules per gram degree centigrade, everything should cancel, grams per grams, delta, or degree centigrade, and I'm going to be left with joules. Now, notice when we plug and chug and put that through our calculator, it's going to require 34.998 joules. Okay, here's what you need to be thinking about. Did the system gain energy or lose energy, or in this case, gain heat or lose heat? What's the label here? Is it positive or negative? Positive, therefore it's endothermic. It required energy or heat. Okay, so think about that, makes sense. If I'm going to heat an object up, if the system's going to gain heat, it's got to put heat into it from the surrounding. So it's going to be endothermic. Right? In this case, it's moved from the surrounding to the system. So that should be a positive value, and it is. If the heat was given off by this, from the system to the surrounding, it would be a negative value. Okay, so it would be exothermic. This is a process that requires energy, so I have to have some form of energy source to add 34,998 joules to the iron to get it to 400 degrees centigrade. Does that make sense? Okay. So again, depending on the metal, it's going to depend on the amount of energy required to move that much heat. Okay? And that's all from the heat capacity that we saw, or excuse me, the specific heat that we saw tabulated on the previous one. Now, this is one I want you to engage with me on, because I have a couple of these on our worksheet today. And if you're not following along, you're a little bit sideways. I don't think this one's that difficult. This is one I would call plug and chug. All we had to do, as long as we memorize the equation, as long as we know that delta T is final minus initial, we're golden. Okay, that's just plug in the numbers. Very simple algebra. I don't think that's very complex. The words are going to be complex because you're probably not used to them. But as far as plugging it in an equation, I don't think that's very demanding of you. The next one, though, you have to think about what's going on. Okay? Because I started the class saying that heat always flows from a hot object to a cold object. So the hot object is going to be getting colder. The cold object is going to be getting hotter. So I need to think about initial and final. Okay? So this is what we need to think about. We're going to have heat flow from one object to another object. Okay? So the heat lost by the hot object has to equal the heat gained by the cold object, assuming that we didn't have some escape to the surrounding. Right? It does make that assumption. But for the most part, we're going to say no. All of the heat moved from the log to my body when I was by the fire. Okay, I didn't get out to the surroundings. So notice this: mass, mass, specific heats. Okay, specific heats. Delta T, but they're different delta T's. That's a little bit confusing. Notice the hot object change in temperature is initial minus final. Why? Well, think about this. The hot object is actually going to get cooler. Okay? Yes?
So if you look at the same order, you take the absolute value?
No. That's a good question. No. You actually do have to have them reversed. Yeah, that's a good way of thinking that, but no, it doesn't work on this one. Yeah. So the hot object is initial minus final because it's cooling down, if it's on, again, going to be on the left side. And the cold object is final minus initial, okay? Because it's now heating up. You're basically doing this, okay, or this, but you're moving heat. So just keep that in mind. The hot object is initial minus final. The cold object final minus. You'll be golden on these. All right. So as you work through these on these problems, so let's see how this works. 76.3 grams of an unknown metal at 100 degrees centigrade is added to 80 grams of water with its heat capacity here to 21 degrees C, the final temperature of the mixture is 29 degrees centigrade. What's the specific heat of the unknown metal? That's kind of cool. Because now I can, if I don't know the metal, and if I can actually do this work, calculate this, I can go look up on the table and say, oh, this unknown metal is whatever. All right, so it's actually kind of a neat thing, practical, that we can actually do in a laboratory setting. But here's what we need to know. Which one of these is the hot and which one of these is the cold? Because remember, back here, a hot object is initial minus final, the cold object is final minus initial. Okay? So over here, unknown metal, when the unknown metal, 100 degrees is added to 80 grams of water. Oh, so the hot object actually became 21.7. Huh, water, oh, that's kind of interesting. Or excuse me, not 29.5. Because the final temperature of the mixture, so it went from 100 to 29.5. The water went from 21.7 to 29.5, so it got hotter. See how that's different? One's cooling down, one's heating up, they're equilibrating at 29.5 degrees. So when I plug this in, I know that the mass of the hot, okay, here, times the heat, the specific heat, initial minus final, mass times specific heat, final minus initial. So if I plug all that in, and you can see that, let's see, did I actually do it? I thought I actually did this one. Where'd it go? Oh, there it is. Okay, so unknown metal, blah, blah, blah. I don't know why it became bold. Okay, so when we solve for this, we're going to solve using this. Here's what we don't know. We don't know the specific heat of the metal. So we're going to have 76.3 grams times the specific heat, which we're going to solve for. 100 minus 29.5, again, initial minus final, because it's the hot object, it's the hot metal. On the other side of the equation, we have 80 grams of water, we have the quantity of water, we have its specific heat. It's going to go from 29.5, it ends at 29.5, started at 21.7, which is final minus initial. So the specific heat of this is going to be 0.485 joules per gram per degree centigrade. Okay? And so again, we can go look at our table, and let's see if we can, I don't know how far back that table is, 4.485. So let's see if we can find that table real quick. 0.485, I just wonder, 0.485. It doesn't look like it's on there. It'd be fun to see what that actually was, because that's all we're doing. Yeah?
So this is kind of similar to like the dilution equation.
Yes.
Because you're
It's just a little more complex. Yeah.
You're like diluting across mass and then specific heat of it on.
And it's exactly the same ratio idea, right? This is to this as this is to this. It's just a little bit more complex.
Like you actually do have something there that is moving and then has like a solubility.
Yeah.
That's like heat.
Yeah, that's a great way to think about that. Yeah, exactly. Okay, questions on that? Because that's it for today. We'll talk about Hess on Wednesday. I'll leave this up here if you want that one. You might need that one for this. I'll leave that up there. Pretty much, you don't need any table for this one. It's all, I have it all on here for you.